Hello! This will be a demonstration of Proposition 20 of Book 6 of Euclid's Elements, which says that similar polygons are divided into similar triangles, which are equal in number and are to each other just as the whole polygons are to each other. And finally, that the polygon has to the polygon a ratio duplicate of that which the side has to the corresponding side. There's a lot to be proved within this proposition, which is why I'm going to break it up into two parts. So that's why right now you don't see a therefore, etc. and a QED, but you're going to see those in a little bit. So what we're given is two similar polygons, A, B, C, D, E, and F, G, H, K, L. I'm going to draw them real fast. Like that. A, B, C, D, E. And another polygon which is similar to it, we're going to call it F, G, H, K, L. Now, as for why Euclid chooses in particular 5 sides, I'm frankly not exactly sure, but it doesn't really matter because you can just as easily prove this if the polygons have 4 sides or 6 sides or any number of sides. This proposition is generalizable to polygons of any number of sides. Okay, so we've got the two polygons here, A, B, C, D, E, and F, G, H, K, L, and we're given that they're similar to each other. And that's it. All we're given is that the two polygons A, B, C, D, E, and F, G, H, K, L are similar to each other, and we're going to prove from this that they are divided into an equal number of similar triangles which are to each other just as the whole polygons are to each other. And finally, that the polygon ABCDE has to the polygon FGHKL a ratio duplicate of that which AB has to FG. So you see that AB corresponds to FG. Okay. We're going to begin by joining 4 straight lines by the first postulate. We're going to join BE, EC, GL, and LH. And we see that we've divided the two polygons into triangles. Now, knowing that the polygon ABCDE is similar to the polygon FGHKL, we can say that the angle BAE is equal to the angle GFL, right? Because they're similar in definition 6.1, similar polygons are equiangular. So the angle BAE is going to be equal to the angle GFL. And also because they're similar, the sides about the equal angles will be proportional, so that BA is to AE just as GF is to FL. So again, BA is to AE just as GF is to FL. Now, knowing that the angle BAE is equal to the angle GFL, and that BA is to AE just as GF is to FL, we have the two triangles BAE and GFL, which have one angle equal to one angle, and the sides about the equal angles proportional, which means that these two triangles are similar triangles. So that we can say that the angle ABE is equal to the angle FGL, and that EB is to BA just as LG is to GF. And of course, we can say that the two triangles have one angle equal to one angle and the sides about the equal angle proportional. We can say that these two triangles are similar to each other by proposition 6.6, which is the side angle side similarity theorem. Not to be confused with 1.4, of course. Now, knowing that the angle ABC is equal to the angle FGH, again, because the two polygons ABCDE and FGHKL are similar, they are equiangular, so the angle ABC is going to be equal to the angle FGH. But we've just shown that a part of it, ABE, is equal to a part of the other, FGL, which means that combination 3, we subtract equals from equals, the remaining angles will be equal, so that the angle EBC is equal to the angle LGH. Excuse me. Now, knowing that EB is to BA, just as LG is to GF, right? We had shown that in step 3. but also by virtue of the polygons being similar, again, the sides about the equal angles are proportional. So we can also say that AB is to BC, just as FG is to GH, which means we have two proportions which have a common term, namely this AB and FG term, which means by proposition 522, xi quality the magnitudes shall be proportional, so that EB is to BC, just as LG is to GH. So proposition 522, if you have any number of magnitudes and an equal number of other magnitudes of the same type and taken two and two together, they are proportional, then they'll be proportional xi quality. And xi quality, the Greek de su, going through the equal, so we're going across the equal term, which is AB, and we're also going across the equal term FG to compare the two magnitudes EB and BC directly, and likewise the two magnitudes LG and GH directly. So that we can say that EB is to BC, just as LG is to GH. Which means, again, we have two triangles, EBC and LGH, which have one angle equal to one angle. We had shown that the angle EBC is equal to the angle LGH, but the sides about these equal angles are proportional because we've just shown that EB is to BC, just as LG is to GH, which means, again, by proposition 6.6, the side-angle-side congruency theorem, these triangles will be similar, so that the triangle EBC is similar to the triangle LGH. Now we can prove this in a similar manner for the remaining triangle ECD and LHK, but this method shall be identical to the one that's come before it, so there's no need to go through it again. Point is that we can show that the polygons ABCDE and FGHKL are divided into triangles which are equal in numbers, so we have three triangles composing the polygon ABCDE, and likewise we have three triangles composing the polygon FGHKL. So the triangles into which the polygons are divided are equal in multitude, as Euclid puts it. There's the same number of them. But we've also shown that these triangles are similar to each other, so that the triangle ABE is similar to the triangle FGL, that the triangle EBC is similar to the triangle LGH, and finally, we can show that the triangle ECD is similar to the triangle LHK, which means we've proven the first part of this proposition, that similar polygons are divided into similar triangles which are equal in number. Now, this being only the first part of the proposition, there is the second part, of course, to come. So I will put a cut here and move on to the second part of proposition 620. So now moving on to the second part of this proposition, it's step 8. We're going to join the two straight lines AC and FH. We can do that by postulate 1, of course. Now, the angle ABC being equal to the angle FGH, again, the two polygons are similar, so they're going to be equiangular. So the angle ABC is equal to the angle FGH. And in addition to this, the sides about these equal angles are going to be proportional, so that AB is to BC just as FG is to GH, which means that with the two triangles ABC and FGH, we have one angle which is equal to one angle, and the sides about the equal angles proportional. So by proposition 6.6, the side-angle-side similarity theorem, these two triangles will be equiangular for one. So the angle BAC is equal to the angle GFH, and that the angle BCA is equal to the angle GHF. Now, the angle BAM being equal to the angle GFN, for these are merely the angles BAC and GFH, we can observe that. And having shown earlier that the two angles ABM and FGN are equal to, or are also equal to each other, right, because they're merely the angles ABE and FGL, which we had shown in step 3 to be equal. With the two triangles, ABM and FGN, they have two angles which are equal to two angles, which means by proposition 132 and some other stuff, that the third angle will be equal to the third angle. So we can say that the angle AMB is equal to the angle FNG, like that, which means that the triangle ABM is equiangular with the triangle FGN. Now we can show in a similar manner that the triangle BMC is equiangular with the triangle GNH. The argument is much the same though, so I won't care to go through it right now. And so the triangle ABM being equiangular with the triangle FGN, by proposition 6 for the angle similarity theorem, we can say that AM is to MB just as FN is to NG. And also, because the triangle BMC is equiangular with the triangle GNH, BM is to MC just as GN is to NH, which means X equality by proposition 522 that AM is to MC just as FN is to NH. So we're hopping across this equal term BM here, and we're hopping across this other equal term NG to compare the extreme magnitudes directly to each other. So AM is to MC just as FN is to NH. But we see that AM is to MC just as the triangle ABM is to the triangle MBC, right? Because these two triangles, ABM and MBC, are under the same height, which means by proposition 6.1, they are to each other as their bases. So AM is to MC just as the triangle ABM is to the triangle MBC. And also, again, by 6.1, the two triangles AME and EMC being under the same height, they are also to each other as their bases. AM and MC are to each other, which means that the triangle ABM is to the triangle MBC, just as the triangle AME is to the triangle EMC. That's just by proposition 5.11. Both of those ratios are equal to they're equal to the same ratio AMC, which means they're equal to each other. And by proposition 5.12, that if you have any series of proportional magnitudes, as one of the antecedents is to one of the consequents, so the sum of the antecedents will be to the sum of the consequence, we can say that the triangle ABM is to the triangle BMC, just as the whole triangle ABE is to the whole triangle, CBE. And so the triangles ABE being to the triangle CBE, just as the triangle ABM is to the triangle BMC. Again, by 5.11, we have two ratios which are the same to the same ratio, which means they're the same with one another. So that again, AM is to MC also, just as the triangle ABE is the triangle CBE. Now we can show in a similar way, again, the argument is much the same, so I won't go through it, just as Euclid had not gone through it. We can show that FN is to NH, just as the triangle FGL is to the triangle GLH. But it was shown above that AM is to MC, just as FN is to NH, which means again by proposition 5.11 used twice here, we can say that the triangle ABE is to the triangle CBE, just as the triangle FGL is to the triangle GLH. And alternating this proportion by proposition 5.16, we can say that the triangle ABE is to the triangle FLG, just as the triangle CBE is to the triangle GLH. Now, if we join the two straight lines BD and GK by postulate 1 again, we can show in continuous proportion that the triangle BEC is to the triangle LGH, just as the triangle ECD is to the triangle LHK, and just as the triangle ABE is to the triangle FLG. So all of these triangles between the similar polygons are proportional to each other, which means again by proposition 5.12 that if you have any number of magnitudes which are if they're all proportional, then as one of the antecedents is to one of the consequents, so the sum of the antecedents will be to the sum of the consequents, we can then say that the triangle ABE is to the triangle FLG, just as the triangle ABE plus the triangle BCE plus the triangle ECD is to the triangle FGL plus the triangle GLH plus the triangle LHK. But it's very obvious that the triangle ABE plus the triangle ECB plus the triangle ECD add up to the whole polygon ABCDE. And similarly, the triangle FGL plus the triangle GLH plus the triangle LHK add up to the whole polygon FGHKL. So we can replace these sums with their respective polygons to say that the triangle ABE is to the triangle FGL, just as the whole polygon ABCDE is to the whole polygon FGHKL. And this is the third thing which we set out to prove. We had also set out to prove that the triangles into which the similar polygons are divided are to each other in the same ratio as the whole polygons are to each other. And we've just shown that, which means we're actually almost done with the proposition. There's one more thing that we must prove within this proposition, and that I will leave to a third section of the video. Finally, proving the last part of this prop, we know that the triangle ABE is to the triangle FGL in a ratio duplicate to that which AB has to EF. We know this by the previous proposition 619, that similar triangles are to each other in duplicate ratio to their corresponding sides. So the triangle ABE is to the triangle FGL in a ratio duplicate to that which AB has to FG, or my bad, yeah, FG. But it was shown in the previous step 17, that the triangle ABE is the triangle FGL, just as the polygon ABCDE is to the polygon FGHKL, which means we have two ratios which are the same with the same ratio, which means by proposition 511 they are the same with one another, so that also the whole polygon ABCDE has to the whole polygon FGHKL a ratio duplicate to that which AB has to FG. And this being all that we set out to prove, we are therefore done with the proposition, therefore, etc. Q, E, D. For closing out the video, I must mention the aporism appended to this proposition, which says that it can be proven in a similar manner that similar quadrilaterals are to one another in a ratio duplicate to that which their corresponding sides have, which means that generally similar rectilineal figures are to each other in a ratio duplicate to that which their corresponding sides have to each other. This, again, I explained at the end of proposition 619 when talking about that aporism, but understanding area as a squaring process numerically, and duplicate ratio also being a squaring process numerically, it makes sense that areas are to one another just as the duplicate ratios are. That being all I have to say about this proposition, I'll end the video here and move on to proposition 621.